Hey, welcome to The Explainer. Today we are diving deep into something we use every single moment of our lives, electric current. And I gotta tell you, the way it actually works, well, it might just shock you.
So, let me start with a question, a real head-scratcher. You flip a switch, and boom, the light comes on instantly, right? Of course it does. But what if I told you that the tiny little particles making that light turn on are actually moving slower than a snail? Seriously, how on earth is that even possible? So, how are we going to unravel this mystery? Well, here's our game plan. We're going to start with the absolute basics. What even is current? Then we'll take a little journey, a microscopic one, inside a wire. After that, we're going to build a really powerful formula from the ground up. And finally, we'll pull it all together with a super fast recap to make sure you absolutely nail your exams.
Okay, first things first. To even begin to tackle our big question, we have to get really clear on what we mean when we say electric current. Think about it like this. Picture a highway. The current, which we call I, isn't about how fast one single car is going. Nope, it's about counting how many cars, that's our total charge, Q, pass a specific point on that highway over a certain amount of time, T. It's the rate of flow, not the speed of an individual. And the way we measure this traffic flow is with a unit called the amp, or amp for short. So if you have 1 amp of current, that just means 1 coulomb of charge is cruising past your checkpoint every single second. Simple as that. And this is where things get pretty wild. 1 single coulomb of charge? That's not just a handful of particles. We are talking about more than 6 quintillion electrons. That's a 6 with 18 zeros after it. It's an absolutely mind-boggling number of electrons all moving together. So in a real-world circuit, how do you measure this enormous flow? Use a tool called an ammeter. And listen, for your exams, this is a big one. You have to connect it in series. That means it needs to be part of the main path of the circuit, so that every bit of charge has to flow through it to be counted.
All right, so we know what current is on the big scale. Now let's do something cool. Let's zoom in, I mean way in, down to the microscopic level to check out the secret life of the electrons inside that wire.
So if you just have a regular piece of wire, the electrons inside are in absolute chaos. They're just zipping around, ping-ponging off everything with no rhyme or reason. But the second you hook up a battery, everything changes. The battery creates this electric field that acts like a drill sergeant, shouting, "All right, everyone, get in line and start marching." And that organized collective shuffle in one direction, well, that's our current. But don't get the wrong idea, this is no sprint. The electrons are constantly bumping into atoms, stopping, starting, and changing direction just a little bit. So we can't really talk about their individual speed. Instead, we talk about their average speed as a group. And this slow, steady, collective movement is what we call the drift velocity. This concept is the key to solving our entire mystery.
Now, what's really amazing is that we can describe all of this microscopic action with one single, incredibly powerful formula. But look, we're not just going to memorize it. No way. We're going to build it step by step so you understand exactly where it comes from.
Okay, step 1. Let's imagine a small cylinder or slice of the wire. In just 1 second, the electrons will have drifted a certain distance, right? We'll call that distance VD. So the volume they sweep through is just the area of the wire A times that distance, VD. Step 2 is figuring out how many electrons are actually inside that little cylinder of wire. Well, every conductive material is packed with a certain number of free electrons per unit of space. We call that N, the charge density. So we just multiply that density, N, by the volume we just found.
Next up, we need the total charge. And you know what? This is the easy part. We have the number of electrons, so we just multiply that by the charge of one single electron, which we call Q.
And here we are. Remember our very first definition? Current, I, is the total charge that flows past a point per second. And since we just calculated the total charge that moves in 1 second, boom, we've done it. We've derived the formula I equals NQ/AVD. What's so amazing about this is how it perfectly connects the big picture current that we can measure with an ammeter to the tiny, slow secret life of individual electrons. All right, theory time is over. Let's put our shiny new formula to the test with a real-world example. And finally, get an answer to that question we started with.
Okay, so here's the setup. We're going to calculate the drift speed for a totally normal copper wire. It's carrying a current of 1 amp,
And we're just going to use the standard, well-known values for how dense the electrons are in copper, the charge of one electron, and the wire's cross-sectional area.
So we rearrange our formula a little bit to solve for drift speed, plug in all those numbers, run the calculation, and get this. The average speed of an electron is just 0.07 millimeters per second. That's not just slow, that is ridiculously, unbelievably slow.
So here it is, the big reveal, the solution to our mystery. The light turns on instantly, not because one electron makes a mad dash from the switch all the way to the light bulb. That would take forever. Instead, the moment you flip the switch, the electric field is established through the entire wire at almost the speed of light. It's like having a pipe that's already completely full of marbles. The second you push one marble in one end, another one pops out the other end instantly, even though each individual marble only moved a tiny, tiny bit. That's electricity.
Now that we've cracked the speed paradox, let's clear up one final thing that trips a lot of people up, especially on exams. Which way is the current actually flowing?
Okay, pay close attention here, because this is a weird little quirk of history. We know electrons are negatively charged, so they're actually attracted to the positive terminal of a battery. They physically flow from negative to positive. But way back in the day, before we even knew about electrons, scientists just guessed and said that current flows from positive to negative, and that convention stuck. So on every single circuit diagram you will ever see, the arrows for current point from positive to negative. It's called conventional current, and it's the exact opposite of which way the electrons are actually moving.
Phew, we've covered a ton of ground. Let's do a lightning-fast recap of the absolute must-know, non-negotiable takeaways you need to have locked and loaded for your exams.
All right, here's your cheat sheet. You need to know those two key formulas, inside and out. You must understand the core concept that solves our paradox. Electrons move slowly, the electric field that pushes them is basically instantaneous. Know the difference between conventional current and electron flow, and please, whatever you do, do not forget, the ammeter always, always goes in series. And that leaves us with one last thing to think about. We just discovered this hidden world of incredibly slow-moving particles that create the instant effects we depend on every single day. And it really makes you wonder, doesn't it? What other secret, slow-motion worlds are out there, quietly creating the fast-paced reality we all experience?